Thank you. So this is a joint work with Erwin, Casey, and Mate, and the talk is about forbidding event cycles, but a special type of event cycles, those event cycles which have uncrossed edges. So I will make it more precise. So first of all, let's define a geometric K and N in the following way. Let's say the vertices are 1, 0, 2, 0, n0, 1, 1, 2, 1, n1, so they are just above each other, and every edge is just a line segment connecting the points here, connecting a point from A and a point from B. So this is what we call as a this embedding of K and N is what we call as a geometric K and N for the rest of the talk. And let's say F is a family of subgraphs, or family of graphs which embed inside geometric K and N. And geometric Turan number is defined as the maximum number of edges you can take without containing any subgraph from the family. This is just a classical definition. And so I'll just mention that so this setting has been studied for paths. So there are some results known about geometric Turan numbers of paths. And Jarfash, by Grass, Caroy, and Walter, and Jarfash studied Ramsey type problems in this setting. But I won't go into it because of the limited time. So there are 6 types of there are 6 different cycles of length 6 which are subgraphs of this geometric K and N. So depending on the order of the top 3 vertices and the order of the bottom 3 vertices, it's easy to see that these are the 6 different types of 6 cycles we have. Now the 3 cycles on the right, these have 2 uncrossed edges, and the ones on the left are just obtained by reversing the order of the top 3 vertices here. So it's easy to see that if we reverse the order of the top 3 vertices, then we would get this one. Similarly for this and similarly for this. Now, whatever these 3 6 cycles are what we called uncrossed 6 cycles, and these 3 6 cycles are what we call crossed 6 cycles, or we just denote them by C6U. These 3 6 cycles are denoted by C6U because they have 2 uncrossed edges. And we will study what happens if we forbid. So if we forbid all of the 6 cycles, then by a classical result of Bondi and Shimonovitz, we know that the order of magnitude is n to the 4/3. And this order of magnitude is sharp because there are C6 free graphs with n to the 4/3 number of edges, with omega n to the 4/3 number of edges. So what we will show is that actually you can get the same order of magnitude if we just forbid the 3 C6s on the right. Again, the same construction works. So that will be the main result. So this constant is not important. We didn't try to optimize the constant. Actually, we will see in the proof that there is some room to improve the constants. But the main thing is the order of magnitude is still n to the 4/3, even if you forbid just 3 cycles instead of forbidding all 6 cycles. And actually, if you notice that forbidding these 3 is equivalent to forbidding these 3, because if we take K and N, a graph which avoids the 3 cycles on the right, and then reverse the order of the top vertices, then the resulting graph would avoid these 3 cycles. So these 2 are equivalent. So as a corollary, we would also get that forbidding the other 3 also gives the same order of magnitude. So forbidding the three things on the right, three C6s on the right or 3 C6s on the left, you get the correct order of magnitude n to the 4/3. And this can be translated to the forbidden submatrix language. Actually, this is equivalent to the forbidden submatrix, to the language of forbidden submatrices. We just have to imagine, so these vertices are on the rows, and these vertices are on the, so these vertices are on the column, these vertices are on the rows, and we put a 1 if there is an edge, and we put a 0 if there is not an edge. So this is exactly equivalent to saying that if we have these 6 matrices, then forbidding M1, M2, and M3, you would get the maximum weight of such a 0, 1 matrix is at most this. So I mentioned this because this is connected to results of Pak and Tardosh, where they forbid 4 different patterns which are not. So the 4 patterns what they forbid are different from the 3 patterns what we forbid. One doesn't imply the other, and they also forbid a different class of and they also forbid more, and they prove big O n to the 4/3 result, and that problem is connected to the unit, is related to the unit distance problem. So their motivation was from the unit distance problem. So, but it is interesting that there you would need 4 patterns and a bunch of other patterns to get the same order of magnitude, but here only 3 are enough to get the n to the 4/3. So the proof idea is to count different kinds of 3 paths. So let us say that from now I will just call this as the reverse end path, and this is the end path, and this is the 3 path. I wrote type 1, type 2, type 3, type 4, but I won't be able to remember this, so I will just call this as n, and this is reverse n, and this is the right type path, and this is the left type path because it opens to the right, and this so well, it is to the right and this is to the left. Okay, the idea is to count the number of 3 paths. So total number of 3 paths is the number of paths of this type, this type, this type, and this type. Now notice that we cannot have too many paths of this type or too many paths of this type, because whenever whenever we have a path of this type, let's just mark this vertex and this vertex. Now just the end vertices, and between a given pair of end vertices you can have at most 1 path of this type, because if you draw another path of this type, then you will have 2 uncrossed edges immediately, and that is forbidden. So the number of paths of this type is n squared at most, and number of paths of this type for the same reason, by symmetry, is also at most n squared. But the difficulty lies in bounding the number of 3 paths of these 2 types. So let us introduce some notation. Let Rxy be the number of, so if we fix the endpoints xy, let Rxy be the number of paths of this type with the endpoints x comma y, and let Lxy be the number of paths of this type with the endpoints x comma y. Then clearly the total number of paths of type 3 are just the sum over all the pairs xy, and clearly the number of paths of type 4 is just the sum over all the paths of this type with endpoints xy. So we want to so the idea is to first obtain an upper bound on the total number of 3 paths, and then so we already know, as I said, we already know these 2, and we want to upper bound these 2. And for that, the idea is to count the number of C6s in the graph in 2 different ways. We basically double count the number of C6s in the graph. Notice that any 2 paths of this type with the same endpoints either create a C6. Okay, I have to show it. Yes. So any two paths of this type with the same endpoints, they either create a C6 of this type or a C6 of this type. Because if you look at if we put together two paths of this type, then we either get this one or, as you can see, this one. So these are the two possible C6s that you can get by, if there are two paths with the same endpoints of this type, then it will be either what we call a self-crossing C6 or a right-hand cross C6, so basically this one or this one. So this is a little bit crude, but it is enough that the number of C6s is at least this much, because for any two paths of this type, you get a unique C6, so the total number of C6s is at least this much. Now we have to upper bound the number of C6s, the total number of C6s. Of course, the number of allowed C6s are these three. Now we just have to upper bound each one separately. Now number of C6s of this type, for each C6 of this type, let's associate the upper middle vertex and the lower middle vertex, and how many C6s are associated to the same pair. It's at most one, because there is at most one, as we noticed before, there is at most one path of this type between a pair of vertices, and there is at most one path of the reverse n type between a pair of vertices. So it is easy to see, it requires some work, but it can be proven that the number of this kind of C6s is at most n squared, and this kind of C6s are at most this much and this much. Just to see that the number of right-hand cross C6s is at most this much, again, let us associate the upper middle vertex and the lower right vertex, and between them there is an n, path of type n, as you can see, and that is between a pair of vertices we can have at most one path of type n. So if there are many C6s associated to this pair, the upper middle one and the bottom right one, then they all have to, then those C6s they only differ in these paths, in paths of this type. So it is easy to see that the number of this type of C6s is this much, and number of this type of C6s is this much. So I didn't want to go into the details, but this can be checked. So now combining the number of, this gives us the total number of C6s allowed is this much, and without loss of generality you can assume that number of these types of paths are more than the number of these types of paths. So we finally get that the number of C6s is at most this much. Now combining with the lower bound that we had, so this is the upper bound on the number of C6s, this is the lower bound on the number of C6s. So here we use Cauchy-Schwarz inequality, and we just solve it. This inequality will give you an upper bound on P33, so the number of paths of type 3, and so the total number of 3 paths is at most, just by adding up, it's at most this much. And there is a lower bound on the number of 3 paths, which is e cubed over n, where e is the total number of edges that you can have. So combining, you would get that the number of edges you can have is at most some constant times 10⁴. So this is the proof. Basically, the idea is to double count the total number of C6s that are allowed. Okay. Now, interestingly, if you only 4-bit cycles with 2 uncrossed edges, then a lower bound of n to the 1 plus 1 over k can be proven for every k. And so this is surprising because in the classical HUN-REN theory, the n to the 1 plus 1 over k lower bound is only known for the cases 2, 3, and 5. But here we can get it for every k. And the idea, we use generalized seed-on sequences called BK sets, which are just a set of numbers, so that every k-sum is different in it. And using that, we can construct graphs which avoid 2k cycles with 2 uncrossed edges. Actually, they avoid a 2k cycle even if it has 1 uncrossed edge. So the only allowed 2k cycles are those with no uncrossed edge is allowed. So it's even stronger. It implies what we want. Here we forbid those with 2 uncrossed edges, but actually the construction avoids those 2k cycles with 1 uncrossed edge also. Okay, so upper bound. So this is a general lower bound, and for the upper bound, we have a slightly better result if the parity is 4k plus 2, and if it is not 4k plus 2, but if it's 4k, then we have n to the 3/2. So I'll show the proof of this one for 4k plus 2. So again, the notation is again the CU 4k plus 2 means, so any 2k cycle, any even length cycle, when we draw it, it has at most 2 uncrossed edges, and this set is those cycles which have exactly 2 uncrossed edges, just as a reminder. So this proof is this proof follows from the okay. So let's say G is a C4k plus 2. G doesn't contain 4k plus 2 cycles with 2 uncrossed edges. Now we will define a partial order on the edges of G in the following way. We say that an edge is less than another edge if they look like this, so that AB is on the left and A prime B prime is on the right, and between them we have one of these 3 configurations. That's when we say that an edge AB is less than an edge A prime B prime. Of course, A is from the set A and B is from the set B, and A prime is from the set A and B prime is from the set B. So now it is easy to see that in such a poset we cannot have a chain of length k plus 1, because if we have a chain of length k plus 1, so we just imagine that these red ones are next to each other, there are k plus 1 of them, then no matter how these red ones are connected, as long as they are one of these 3 types, you can find a 4k plus 2 cycle in the graph. So in this poset, there cannot be a chain of length k plus 1. So there is no chain of length k plus 1, which means that the largest anti-chain has size at least 1 over k fraction of all the edges by Minsky's theorem. Now, this anti-chain has a nice property. It avoids all C6s with 2 uncrossed edges, because if there is a C6 with 2 uncrossed edges in this anti-chain, then there will be, if there is a C6 with 2 uncrossed edges, then it's either this one, or this one, but in all 3 cases, there are 2 edges such that one is less than the other according to this partial order. So this anti-chain doesn't contain, this anti-chain in the poset, the set of edges in this largest anti-chain doesn't contain any 6 cycles with 2 uncrossed edges, and it has size at least 1 over k fraction of all the edges. And by the previous, by the main theorem, this is at most big O of n to the 4th third, because a graph which avoids C6s with 2 uncrossed edges has at most n to the 4th third edges. So this implies that the number of edges is at most big O of n to the 4th third as well. And for the other theorem, we do a similar thing, but instead of defining a partial order like this, you would just define it whenever there is a C4, the left edge is, we just say that whenever there is a C4, that the left edge is less than the right edge. And then by a similar observation, there is not a long chain, and then you will find a large anti-chain, and in that anti-chain is C4 free, so the total number of edges in the graph is at most 10 to the 3 half, big O 10 to the 3 half. So that's the idea for the other one. But probably we do not expect that these are sharp. Probably they can be. The truth is that much smaller is true. That probably at least for small k into the 1 plus 1 over k is true, but we don't know. Yes, and thank you, and happy birthday to Tibor, Gabor, and Andre.